Hello and welcome to another C WinSock networking tutorial. It's been a long time since I've made one of these, and there's actually going to be a lot of changes that I've made since the last tutorial. So first let's look at the server. Now I've uploaded the solution in the description, which you'll need to download because I might forget some things that I've changed. But looking at this, nothing really has changed in the main function. I'm just going through, this is the old, this is the new one, except for we're no longer using that for loop to get up to 100 connections in total. We're just using a while loop, and we don't have that system pause there. So nothing important here has changed. Let's go ahead and look at the header files. So let's start with server header. Now, if you notice, we have some different things. We have a shared mutex in the new one. We're using shared mutexes now. I'll go over that. And we have a lot less header files. This is the old one with all these header files. And then we also have the pragma comment. We're only using the header files that we need to use now. And this helps with compile time, and it just helps with the cleanliness of the code. So in our new one, you see we don't have that pragma comment. And we also don't have the define WinSock deprecated no warnings because we're no longer using that deprecated function in the newer version. So I'm just mentioning that. Let's look at our connection class. Let's see what's changed here. In the old framework, we had this active connection variable. And I had this really kind of backwards way that I was managing the connections. And I'm no longer doing it that way. I wish I hadn't even done that in the series, but for some reason I was thinking that was the best way to go about doing it. There is no longer, in the new one, there is no longer that active connection variable, so we're not even using that. And our ID variable is instead just going to be a unique value in the new server. In the old server solution, it was the actual index inside of the array, but we're no longer doing it that way. Now we're just using, it's just going to be a unique number for whichever connection. Something else is, if you notice, all the member variables are prefixed with m underscore. I was told that this is basically what you should do for member variables, is they should be prefixed. Just to clarify, if I have a function and I have a variable inside the function and I'm accessing variables inside a class, it'll be apparent whether the variable is a function variable or a class member. Now let's look at the server class. So if you notice, a few things have changed. Previously, with stuff like send all, we were sending in the ID of the connection, and this was the index in the array. Now what we are doing is we are sending in a shared pointer to that connection for all of these. Something else is we are using const whenever it is applicable. So if the variable does not get modified, we should be using const because it's constant. So let's see, what else? We have a client handler thread and our packet sender thread are now both taking a reference to the server. So before we were doing it, and then also the client handler thread is taking, a shared pointer to the connection for that client. Before we look into this, because I wanted to show you, before we were using create thread, and now we're actually using the newer version of thread, the std thread. But before we look at that, let's also see disconnect client. It takes a pointer to the connection now, or a shared pointer. And our connections is a vector of the shared pointer of connections. It's kind of ugly to look at, but this is just how I decided to change it to be. we still have our mutex for the connection manager. We have an ID counter. This is just so that we can give each connection a unique ID. And then we have, our same variables, just prefix with m underscore. We have a new boolean to store whether or not to terminate the threads. I'll go over this after we go over how we're using thread in the client handler thread and packet sender thread. And then we have a vector of pointers to all of our threads that we have open. Let's see, was there anything else? Okay, so first let's look. In our old server, we had the pointer to the actual server object called server pointer. However, it's not going to be like that in this one. Let's go ahead and look at our server.cpp. And actually, I meant to look at the server INI, which I don't have in tutorial 12. It was just part of the server PPP, or CPP. So let's look at the constructor, and let's check out a few things that have changed. So first off, before, I had called this broadcast publicly, but that is actually not the right term. What I should have called this was loop back to localhost. So if it's true, then let me make sure I say this right. Yeah, if it's true, then it will loop back to localhost. And I had put this description wrong. I'll fix that before I upload it. But yeah, if it's true, then it will loop back to the same computer, so other people will not be able to connect. If it is false, then we will not loop back to localhost, and then other people will be able to connect. Now, if we scroll down and look at this, you see before we were using create thread, we were calling packet sender thread, and we were setting the server pointer. However, in our new solution, what we were doing is we initialize the ID counter. We create a new thread, and this is PST, it's short for packet sender thread. And you see we pass in the function that this thread's going to run off of, which is packet sender thread, and then we pass in the arguments for that function. Now, let's take a look back real quick. Our packet sender thread took a reference to the server, and in our thread where we're calling it, the way that we'll pass a reference to the server is we'll call stdref, and then we'll pass in dereferenced this. And that'll actually give us a reference to the server. After we do that, we're going to detach this thread. And then our vector of threads, which our vector of threads is in our server class right here. We're going to push back this thread onto that vector. Now the reason that we're calling detach is because if we don't call detach, then as soon as we leave this function, as soon as we get to right here, our program will crash. So we need to detach the thread. I guess let's look at how the connections are managed, because they're a bit different now. We're going to take a look at listen for new connection. So let's see. Yeah, in the new one, I just stored the adder_len variable inside this function. There was no reason to have it as a member of our server class. In the old solution, so what we're looking at right now, it was a member inside of our server, and that was not necessary. So we make our new connection, and that part's the same. Check if it failed. If it's successful, let's take a look at how this is different. So before, we were doing this whole, are there unused connections? Use one of them. If there aren't any unused connections, then, do all this crap. And then after that was all done, we would create the thread. We're no longer using that whole unused connections variable. The way that we're doing this is we're just locking our connection manager. Anytime, this is something I just want to mention real quick, just to clear it up. Anytime that we're iterating through our connections, or, really doing anything with the whole array of connections, I guess, we need to lock our connection manager mutex. So in this case, we're going to be adding connection to the vector. Right here is, let's see, where are we doing that? Right here is where we're adding the connection to the vector. So we need to lock that mutex. Right here is where we're making the new connection. And if you see, we're using a shared pointer. So the way that this works is to do something like this. So our connection constructor just takes in the socket that we're going to be connecting with. And I'm just trying to explain how this shared pointer syntax works just to make it clear. So we're creating a new connection, and then we have to put std make shared, and then we put in the data type, which is connection. And then this is the constructor for that actual connection object, which in our case was a socket. So if I just wanted to make a new connection but not have a shared pointer to it, then this is exactly how this line would look. However, I need a shared pointer, so that's why we're doing it this way. Here's where we're pushing that new connection back into our vector of connections. Here's where we're setting the ID for that new connection, and then we're just incrementing the ID counter. And then we're saying the client connected. Now here's where we're making the client handler thread. If we look at the old version, this create thread is where we were making that thread. And what we're doing is we're creating the thread, and let's take a look at that constructor again. The client handler thread right here, it takes a reference to the server, and then it takes the actual shared pointer to the connection that the client handler thread will be using. So we are passing in the reference to the server, and then we are passing in the shared pointer to that new connection. We are detaching the thread because otherwise the program will break as soon as we exit the scope. And then we are pushing that thread back to our vector of threads, which we'll go over why we're doing that in a little bit. Right here, I'll go ahead and go over that actually while it's fresh on our minds. When we call the server destructor, we want to make sure that all of the threads have ended. So what we do is we check if our terminate threads variable is true, and if it is, then for each thread that we have, this is just like a for each loop. It's basically saying for each thread, and we're going to reference that thread by saying t inside of m underscore threads. T join is just saying wait for that thread to end. So if you're not familiar with the for each loop, it looks like this. So in a sense, these two do the same thing, but this is just a bit cleaner, since we don't have to, re-reference m underscore threads. Now, if you notice, for example, let's look in our process. I moved the process packet function to its own CPP just because it's going to be our biggest function. It's got to be able to process all these different packets. And what I'm doing right here is I am iterating through the connections with these types of loops now. So, for example, when a user sends a message, we are creating a chat message from our package structs, and we're creating a message packet from that. And I'll go over this in a minute because I know it looks a lot different from how we had packets before. And then we are going to do shared lock on our connection manager mutex. We're going to go through each connection using that for each type syntax. And then if it's the same user that sent the message, skip. Otherwise, we're going to append that packet to that connection that we're iterating through. So real quick, let's go through our packet manager and our packets. We're going to go through the packets first. So previously, our packets were not very flexible. We had an integer to store the size, and we had a pointer to the actual data, our buffer data. Now how it works is we have all of these append functions which can be used to build our packet, and then we have just a vector of bytes for our buffer. So int 8 underscore t, this is just 8 bits, so it's just 1 byte of data. We don't need a variable for size because we can just get the size by calling mbuffer.size. Now, these append functions, let's look at how these work. So the best way I would say is let's look at the packet structs in our old one and in our new one. So for example, for our chat messages, our old one was like this, right? We had to first calculate the whole packet size. We had to allocate that. We had to we had to make the packet type, get the message size. We had to copy that. We had to copy the message size and calculate the offset. And then we had to copy the actual message with the offset for that. And then we created our packet to be returned, and we returned it. So this is not very friendly when you're trying to make new types of packet structures to be sent, because you have to sit here and do all these calculations, and it's just it's kind of slow, I guess, in terms of development time. It's slow. So the way it works now for that same thing is we create a shared pointer to our packet. We append the chat message packet type. We append the message size, and we append the actual message. And then we just return this packet. So it went from, it went from 9 lines down to 5 lines, and this is more readable, in my opinion. So that's good. Now, in case you're wondering, why are we using a shared pointer to the packet? Here was my thinking for that. Let's say that user A. Let's say we have 3 users. We have user A, B, or no, let's say 5. I think it'll make more sense with 5. C, D, and E. User A sends chat message. Well, if I use a shared pointer to the packet, what I can do is I can allocate packet once, and then I can add shared pointer to D, C, D, and E's packet managers. Okay? However, if I'm not using a shared pointer, let's say we have the same deal. Copy all those lines. We have 5 users, and A sends a chat message. I'll have to allocate packet for user B, then add packet to B's packet manager. Allocate packet for user C, etc. So this basically will help when we have a packet that needs to go out to all the clients, because we won't have to keep allocating it. I know it's a little bit uglier, but we'll just have to deal with that, I guess. This does have, I guess, a disadvantage. If we're creating a packet that only goes out to one user, it's there's no real advantage to using the shared pointer as far as I know. But I'm thinking, in the scope that we're going to have a packet that goes out to more than one user, then we'll get the benefit there. I changed how the file transfer, all of this stuff works. Let's see. So I changed the buffer size just to be 16 kilobytes instead of 8. That's not an important change, really. For the file transfer data, there is now a function called get outgoing buffer packet and a function called initialize. I just did this because it was taking up too much space in the process packet CPP. So if we look at that CPP, pulling it up on the old one and the new one. Okay, in the old one, when they requested a file, this was just for the initial file request. There was all this code in the process packet CPP, and it just took up a lot of space. So I changed it so that what we do now is we call initialize, and then we pass in the file name, and we pass in reference to somewhere to store an error message in case something fails. And if it's successful, then we append the next bit of that file to send from the get outgoing buffer packet. I'm not going to go too much into this because I have a solution if you want to look through it. This isn't. I don't really feel like this is new material. I just don't want to just upload a solution and say, hey, you guys, this is a new solution. I'd rather actually go through and explain some of it. So if the initialization failed, then we'll send that error message that'll get filled by initialize. And it's a lot cleaner, I think, than the old way that we were doing it. It's a lot less to look at and think about. And then for the transfer request next buffer, we basically just make sure that a transfer is in progress, and as long as it is, then we just get that next outgoing buffer packet. Now let's look at how the packet manager works now. The old packet manager used packets. The new packet manager uses shared pointers to packets. I think that's the only real difference. I can't think of if I had really done anything else. I'm just checking. Yeah, I think that's about the same. Now, one thing that's a lot different is if we look at our packet sender thread in both of these. Okay, in the old one, this was a big flaw. We are iterating through all of our connections, but the problem is we are not locking our connection manager mutex. In our new one, first we're checking if we need to terminate the threads. If for some reason I have it where if the server, I guess, destructs. Let's look at the server destructor. Where is that? Where did I have that? Oh, I don't want to waste too much time looking for it. Yeah, the server destructor. You see we set terminate threads to true. So in our packet sender thread, gotta find where that went to. Here we go. In our packet sender thread, the first thing we check is, basically if the service destructor got called for some reason, we'll need to be exiting this loop. Otherwise, we're going to go ahead and lock the connection manager. We're going to iterate through all of our connections, and if there's pending packets, then we're going to get the next packet to be sent out. And if you notice, we're using a shared pointer here. In that way, again, we don't have to copy a bunch of data. Here we are, this is the syntax we'll never have to repeat this because the only place that we should be calling send all is in the packet sender thread. But that's the syntax. We're just passing the address of the very first byte in our vector, in our buffer. And I just want to make it important that if we were not locking right here, we could have an issue because if we're iterating through and let's say that one of the connections gets removed at the same time that we're iterating through, we could have really strange things happen. And that's why we need to make sure that we lock our mutex, because the pointers could be getting moved around while we're iterating through. Something else I almost forgot to cover is we're using a shared mutex now. So inside of our server class, our mutex for the connection manager is a shared mutex. What that means is we can use it like a normal mutex, where if we look at when we're accepting a new connection, for example, we just use lock guard right here. However, what we can also do is, let's say for our client handler thread, for example, let's see, where is that? Or I guess first our packet sender thread, we are using a shared mutex here, or a shared lock, I mean. And the other place we are using a shared lock is inside of our process packet. So anytime that we want to iterate through our connections and we're either receiving or sending data, we can use a shared lock and they won't wait for each other. So I'm trying to think of the best way to explain this. Basically, if we want to be able to read data and try to send data at the same time to our connections, we'll use a shared lock. Because if it's locked in, let's say, the packet sender thread with the shared lock, and we use shared lock here, it won't wait until it gets unlocked. They'll just share the lock. While whenever somebody disconnects and we try to call a lock, for example, let's see, where is disconnect client at? Right here. When we call a normal lock on it, this will actually wait until the shared lock is released, and this will lock. While this is locked, we will not be able to do a shared lock. The shared lock will wait until this lock guard drops itself, which will happen when we exit the scope. Okay, so let's go ahead and look at the client. Now with the client, we are now actually using the packet manager in the client. Before we were not, which was an issue because, we have the main function where the client has its initial thread and it can send data that way. But then we also have our client handler. Let's see, what did I call it? I guess we just have our client thread function, which is in its own thread. So both of these threads can send data. Because of that, we need to use the packet manager. A lot of the changes I had made to the server also apply to the client. So the client no longer uses create thread. Instead, it uses std thread, and we're passing in references to the client in the client thread and packet sender thread. I changed a lot of these just to use constant where applicable. I had changed to where we're only using the headers that we need to use instead of just using a bunch of headers. I had changed to only pragma comment the library where we actually need to in the CPP files instead of the header file. And other than that, I'm not really sure what changes I had made. Alright, so that is all that we are going to go over for this tutorial. If you have any questions about the solution, feel free to ask in a comment and I'll try to respond to the best of my ability. We're not going to go over anything else as far as blocking sockets are concerned. We're going to start looking into non-blocking sockets for the future tutorials. Once again, I want to give a big thanks to Reductor for all the help with all of this. I'm going to go ahead and warn you guys, I have never made a non-blocking server and client, so it's going to be a learning process for me as well as for you. I've read up a lot on it, and it seems like a lot of the, a lot of the ways to go about doing things are similar. Like, we're still going to be using send and receive, but we're going to have to, manage when something would block, or if we only get, so much data and we expect to get the full amount of data and so forth. But I don't think it'll be too hard. So that about sums it up. So thanks everybody for watching, and that's all we're going to go over for this tutorial.